It seems like a pretty straightforward thing to do. One takes a sample of the salt and sends out for analysis. But it turns out that obtaining repeatability and proper uncertainty quantification on the result is proving to be more difficult than we expected. And there are really 3 steps to doing elemental analysis of a salt sample. Step 1 is sampling the salt, which is a challenge in and of itself in terms of making sure that the salt sample is representative of the system that it came from. For example, if you're going to use a cold rod technique for sampling, so you sort of like candle dipping into the salt, that seems easy enough. But it's not clear that what precipitates on your cold rod is representative of the rest of the melt, because of course you have temperature dependent solubilities of your solute, so that might not be representative. And then you have other options for sampling that ensure that you're sampling from a homogeneous liquid, or maybe you sample a big chunk and then you grind it and powder it and homogenize it, and then sample 50 milligrams for digestion. So there are a lot of questions around sampling and making sure it's representative. So that's step 1 of elemental analysis. Step 2 of elemental analysis is digestion. So we do elemental analysis by ICP techniques, ICP-LES or ICP-MS, and the input into these instruments are highly dilute aqueous acidic solutions. So we need to go from 50 milligrams of salts to 50 milliliter of an aqueous digest, and we do so with microwave assisted digestion, and that entails bringing a series of acids at controlled pressure and temperature over a period of time, and so that facilitates digestion, and then that digest, which is what you see here, is analyzed by ICP-MS. So there are 3 steps, and what we first started out to do is we proposed that we run a round robin with several groups of elemental analysis and other salt properties, and this was co-organized. We started organizing this during the pandemic, so in 2020, together with Jake McMurray from ORNL and Ted Bessman. Jake McMurray, who was at ORNL at the time, he's now at Kairos Power, and Ted Bessman at the University of South Carolina. And we sent out sodium chloride, potassium chloride, and Flynac. These were purified salts prepared by Oak Ridge. Here they are when they were being stored in our glove box. And then we distributed them out to 22 organizations in 7 countries. And the purpose was to understand how we do error quantification for different property techniques, to share best practices, and maybe to understand what might be good standard materials to make available for salt analysis. So what do I mean by standard materials? When you're looking to do density measurements on your fuel salt, you might want to calibrate your setup, and so you'll order maybe a NIST standard material, and you'll run that standard material, and you should get the known density, and that's your standard material. We don't yet have an established standard material that's of relevance to salt properties, and so by doing round robins, that could be a first step towards, say, establishing a Flynac or sodium chloride, potassium chloride as a standard material. One would have to hold a large library of 1 batch of these, and then that becomes your standard material. So this was toward kind of a first step towards establishing that. And our process for the round robin was to anonymize all of the participants. So once we've sent out the samples, then we generated unique IDs for everyone. And then to request submission of procedures so that there's a chance for a blind peer review of the procedures. This goes towards establishing best practices and sharing best practices. And so we were hoping that this would help in making sure that there's some common level of detail to how the data reduction is described, how the error analysis is performed. And I would say this was useful. In round robin 2.0, we'll probably break this up in smaller chunks so that more attention is paid to each of these steps. So I'm not going to show results from all of the data we received. Sorry. These are sort of the data sets as of a year ago. We have more data sets now, and this is a work in progress, and there's a manuscript being prepared, but I'm not going to show results. It's not within the scope here, but I wanted to show an example of anonymized results for elemental analysis on FlyNAC, specifically for minor constituents. And so here are 3 examples from participants 13, 12, and 11 for ICP OES and ICP MS. And you'll notice, for example, for nickel, the one result is 4,000 ppm and another is 10 ppm. And for aluminum, it's 120 and 50 and 6. And so the error bars are really quite small relative to the variability from sample to sample. So this is a puzzle. We all think that we're running our measurements correctly, so why this variability? And so we're trying to, so this was kind of an observation back in 2021, and we've been trying to work systematically through this 3 steps of elemental analysis. Does it have to do with the sampling? Does it have to do with the digestion, or does it have to do with the way we use standards for the ICP OES, ICP MS techniques? So for example, if we look at, these are different digestion acids with different digestion instruments. And we can look at different ways of doing data validation on the results. For example, if we look at the major constituents, we could say this is FlyNAC. So if we just look at lithium fluoride, potassium fluoride, sodium fluoride, we assume that they're fluorides, we should get 100%, 1 gram per gram of sample. And it turns out that depending on how you do the digestion, the numbers don't quite add up to 100%. So that's telling us that that digestion was incomplete. Another example is looking at different acids. So here you have digestion with nitric and HCl, and this is just nitric, and it looks like these solutes pretty much have no sensitivity to these 2 acid mixtures. But then if you look at digestion with HF and without HF, boron and iron seem to be sensitive to it. And so we're working systematically through these 3 steps of elemental analysis, and this feeds ultimately towards material accountancy, because you need to have a clear understanding of what the uncertainties are on elemental composition in order to propagate that forward into accountancy uncertainties. So that's one of the problems we're working on. I'll pause and see if there are any questions so far. Okay. So the next example I wanted to give is from salt properties, and specifically salt density. So salt density of mixtures could be predicted from molar volume additivity. So for example, if we know the temperature dependent molar volume of uranium chloride, and we know the temperature dependent molar volume of sodium chloride, then we could do a weighted average of the two and predict the density, the liquid density of the mixture of the two. If there's any non-ideality, then of course the density will change. And so it's important to also make measurements on mixtures and to understand the nature of the non-idealities. And then in turn, a measurement of density could tell us something about a change in the composition of your melt. There's a one-to-one relationship between composition of the melt and density of the melt. And fundamentally, this is a really simple measurement to make. You suspend an object in your salt and you can deduce the density of that salt. So it's you don't have, in a sense, it's simpler than elemental analysis because you don't have the sampling step. You can probe in situ, what is the density of this melt? And here's an example of a density study we did with particular focus on uncertainty quantification. And we did this study for FLiBe, lithium fluoride, beryllium fluoride, Li2BF4. And we focused on this melt because there was quite a bit of data and quite a bit of scatter. So the open circles here is prior data, and the closed circles is new data that we collected. And then the dashed line here is the 1974 NIST database value for the density of this mixture. So it's on the upper end of the data that existed already. So the open circles are data that existed already. NIST had picked sort of the upper end of those correlations to deem, to deem as relevant. And what was interesting to us is that the variability in the previous data was quite a bit bigger than the reported uncertainties. So we were trying to understand, is this an experimental artifact that we had so much variability among prior data? Or does it have to do with the mixture was just different? It was a different batch, probably had a slightly different composition. What is the source of this uncertainty? And then most importantly, the thermal expansivity, so the slope of density with temperature was of relevance because thermal expansivity connects to a lot of passive safety features and inherent safety features of molten salt reactors. I put a cross section here of a molten salt reactor. This is the Thorcon molten salt reactor to illustrate, for example, natural circulation. If you have a heat source at the bottom and a heat sink at the top, then that will drive natural circulation. So it's a passive salt flow, which is then a passive decay heat removal pathway. And the elevation difference between your heat sink and your heat source that is required in order to remove a certain power level is directly proportional to the thermal expansivity of your salt. So how tall your vessel is directly proportional to the thermal expansivity. And so if you have a thermal expansivity of 0.95 or 0.4, that's more than twice the building height. So it's quite an important parameter to pay attention to. And so we set out to understand what are the sources of uncertainty and could they explain this variability. And we generated new data, which you see here. It's on the upper end. We looked at heating and cooling cycles in particular, because one of the sources of errors we identified was gas dissolution, and because you have a bobber here that is subject to buoyant forces. If your salt undergoes thermal transients, then there will be gas that is soluble in the salt that will produce bubbles. And these bubbles will contribute to the buoyancy that the bobber experiences. And so the temperature dependent gas solubility then actually impacts the measurements that are being made here. So to correct for that, we would do up transients and down transients in temperatures to make sure that we don't have a bubble formation effect. And that's what you see here. We conclude that there's that we correct for that well, and we think we achieved that through the shape of the bobber that we selected and through allowing for enough time for equilibration. Okay, and so in the end, we were able to achieve a measurement accuracy of 0.3% for density and 4% for thermal expansivity. We also have the isotopics of lithium. They can contribute up to 2% to error because lithium is such a light element that 7.6 can give you an effect on density. And then we also computed the we measured the composition of the salt, so we reported the molecular weight of fly, which is sensitive to composition. Now this becomes a tool for, this sets an example for how one might do error propagation and error analysis. This introduces this new question of gas solubility as a source of error in density measurements. And then it demonstrates to what accuracy we can measure density so that maybe it can be used to back calculate composition of the melt. So in this study, we went to 0.3% accuracy on density, and we think we can improve upon that. So we think we can get to 0.1% accuracy on density. All right, so that was one example of salt property measurements. I'll pause here before I talk about salt speciation and electrochemical techniques. Are there any questions?
I have one question related to your accuracy.
Yes.
Do you know, I mean, that's really good. For when you look at some of your data, you kind of have an idea of how error can drive, like you even gave the example of how error can drive differences in the data and how that can affect engineering of the systems. What would be a sufficient accuracy that's necessary for, for these density measurements? And I know that the accuracy that's necessary for a given measurement, depending on what it's used for, can vary. But I mean, from my minimal experience and that small error, I would say that accuracy for the density is pretty good.
Yeah. So for thermal expansivity, a factor of 2 is not good enough. 4% is probably pretty good because if you get your elevation levels within 4%, that's pretty good. For density, 0.3% is more than fine. Absolute density is not that important in reactor design. But if you wanted to use density to infer composition, then higher accuracy certainly helps you. So with 0.3%, you can probably infer composition of beryllium fluoride, lithium fluoride to about 1 mol%. If you're on a liquid fuel, so if it's sodium fluoride, sodium chloride, uranium chloride, then obviously the the mass difference, the density, the molar volume difference is big there between the two constituents. So 0.3 accuracy on density would give you a sub-mole % accuracy on composition, which is pretty helpful.
Right. Okay, thanks. Yeah, so it's condition dependent, but those numbers seem great.
Yeah, but it's a question of can we push the applicability of density measurements towards inferring composition is what we're asking here. Yeah. Any other questions? So ultimately, if we wanted to know if the composition of a melt has changed, then in a loop, going back to our loop, we could submerge a bobber like this and say, okay, we understand how the composition of the melt has changed because we have a way of so accurately measuring the density of the melt. Yeah. But for a reactor designer, I think even 10% is pretty good on the absolute density. Yeah. Any other questions on density? Okay, so I'll talk about two more topics really briefly on speciation and then electrochemical methods. So this was a collaboration with Mark Asta's group. It was an ab initio molecular dynamics study on structure of FLIBE, and we were interested in solvation of transition metals. And specifically, we were trying to understand how transition metals are solvated, because the existing theory was that dissociated F- is the primary modality of solvating transition metals. And so that meant that a melt like FLINAC, which has a lot of dissociated F, would readily solvate a transition metal, and a melt like lithium fluoride, beryllium fluoride, which may not have as much dissociated F- would maybe have a harder time solvating transition metals. And so what we showed is that, in fact, that image of transition metal solvation was a little narrow. There are multiple modalities of solvating the transition metals. One of them being incorporation into the oligomer structure of melts that form oligomers. And we looked at 3 different types of melts: potassium fluoride, sodium fluoride, which doesn't form strong associates, doesn't form oligomers. We looked at beryllium fluoride, lithium fluoride, so Li2BF4, which forms strong associates between beryllium and fluorine, and which also forms oligomers. And we also looked at a lithium aluminum melt, which also forms oligomers. And we find that there is in FLIBE, Li2BF4 could theoretically be fully associated BF4. It could all be BF4 because of the stoichiometry of Li2BF4. But in fact, FLIBE forms oligomers, so there's sharing of fluorines. And by sharing fluorines means that you also have to have dissociated Fs. So if you have, here you have your dissociation association reaction. If you have 2 monomers, BF4, you put them together, it forms an oligomer, and so it has to release a dissociated F. So if you have oligomers, the more oligomers you have, the more dissociated F you also have. So it turns out that FLIBE actually has about 13% dissociated F, not 0 dissociated F. And then similarly, aluminum fluoride melts will form oligomers, and even though the stoichiometry would allow you to have no dissociated F, in fact, you form oligomers and you have about 15% dissociated F. And then if you look at the solvation, you find that for Cr2+, you have an equal distribution of solvation by dissociated F and solvation by the oligomers. And so why is this all so important? Well, now we have a richer understanding of the fundamentals of solvation. And solvation is important because we need to understand the source terms in the molten salt reactor, and we need to understand what's in solid phase, what's in liquid phase, what's in vapor space. So what's the partial pressure of our species? And so solvation is needed to be able to predict that. And we also need to understand the temperature dependence evolution. So by having understanding what the reactions of solvations are, then we can associate an energy to it and an equilibrium concentration, and then we can describe the temperature dependence. So it helps build the thermodynamic model by understanding the species that form. And so we're building on this new understanding with temperature-dependent electrochemical measurements of solute activity and solute diffusivity to validate this observation that the oligomers play an important role in solvation of transition metals. And this is the validation part is ongoing work. So I'll pause here before I talk about electrochemistry work. Any questions on salt structure and solvation? And this is a concept that I'll use in a moment when I talk about the electrochemical studies. So if you so the terms I want you to go forward with is this concept of oligomer and the complex the context of the concept of oligomer. So the oligomer term, where you have a cation, it coordinates with a number of anions around it, and that forms an oligomer. And then the concept of a monomer, which is just a cation with a set of anions around it. And I'll be using these concepts in a moment here. So any questions so far? Okay. So let's see. How much time do I have? Great. Oops. Okay, so I wanted to give you an example of capabilities of electrochemical measurements. And specifically, we were looking at tritium in FLiBe. We were looking at tritium in FLiBe because tritium is an activation product of lithium and beryllium. And there's quite a bit of variability in data for hydrogen solubility in fluoride melts and hydrogen solubility in FLiBe. In fact, order of magnitude variability in solubility. So we wanted to understand if this variability is due to the oxidation state of hydrogen. Is it H plus or is it H2 in the melt? And is this why previous studies of solubility have so much variability? And in order to do that, we needed to have a technique for measuring solubility that is oxidation state specific, and electrochemistry is one such technique. Otherwise, studies of solubility are typically done in the gas phase. So you'll have a salt annulus, hydrogen is permeable through metals at high temperature. So you'll flow hydrogen on one end and detect it at the other end. And from transient responses, you can back calculate the solubility of the gas in your salt. So you apply the gas, see how long it takes for it to be detected on the other end, and then back calculate the solubility. So there isn't really a good way to be oxidation state specific, unless you control the redox potential, which was not done in these previous studies. So that's what we set out to do. We set out to understand redox state specific solubility and diffusivity. We also looked at the temperature dependence of diffusivity of hydrogen in the melt. So the red data is a diffusivity of hydrogen in FLIBE. And you'll notice that there are 3 data sets. 2 of them have an activation energy of about 40 kilojoules per mole, and 1 has an activation energy of 170 kilojoules per mole. And there's an important meaning to this activation energy because the fluorine diffusivity, fluorine is part of the complex species that exist in salt, in FLIBE. So its activation energy of diffusivity is around 130 kilojoules per mole. So these are probably fluorines that are breaking apart from the complexes and then joining another complex. Whereas the activation energy of lithium diffusivity, lithium is not part of any of the complex structures that form in FLIBE, and its activation energy is around 30 kilojoules per mole. So by looking at the activation energy of diffusivity, we also learned something about the solvation in the melt, and the 3 data sets sort of showed both cases. So we were curious to understand if this is a redox state effect. So maybe the H plus complexes and the H2 doesn't complex, and so maybe this is H plus and this is H2, and that's what we were seeing here. So we were again motivated to use electrochemistry to do redox state specific studies of diffusivity as a function of temperature. And so this was our setup. We introduced hydrogen in the salt, not through neutron activation reactions, but through chemical reactions. Lithium hydride reacts with beryllium fluoride to form H2 or maybe BH2. And so here is an electrochem run, current versus voltage before hydrogen addition, after hydrogen addition. This is hydrogen oxidation. So what we're detecting here is H2, and we're forcing it to oxidation to H plus. So this is the first demonstration of redox state specific detection of hydrogen in FLIBE. And then we were very happy to see that we can detect it. And then here is a titration to show that the more hydrogen we add, the higher this peak is, and there's a approximately linear response to the amount of hydrogen that we're adding. So that's reassuring that we can indeed detect the hydrogen we're adding. There are other checks we can do to make sure that we're looking at hydrogen and not something else. We're not looking at oxygen, for example. We know we're not looking at oxygen because oxygen would be a 2-electron reaction. O2 minus would need to lose, would need to lose 2 electrons in order to oxidize to O2 gas. Whereas hydrogen needs to lose 1 electron in order to oxidize to H plus. And from the peak separation here, we can determine that it's a 1-electron reaction, so it's definitely not oxygen. And then from the potential of the reaction, we also see that it's about where hydrogen would be. So we're pretty sure we're looking at hydrogen here. And then now that we can detect it, we can use electron analytical methods to measure diffusivity and concentration. And so we were able to look at the activation energy. With 2 electron analytical techniques. In one case, we can conclude 30 plus minus 20 kilojoules per mole, and in the other case, we conclude 30 plus minus 20 kilojoules per mole. So either way, we're far from the 170 kilojoules per mole. So 2 conclusions here. We were able to measure specifically H2, not H plus in FLIBE, and conclude that its activation energy is low, so it is not being integrated into the ionic complexes. It's not forming a complex is what we would conclude so far. So we would sort of concur with this data. And then we also believe that we're forming beryllium hydride, which is not an equilibrium compound. It's beryllium hydride thermally degrades at 600 Celsius. But it can form along the way. So if beryllium fluoride reacts with lithium hydride, we could form beryllium hydride, which then thermally degrades to H2 gas. And if we look at the concentration as measured with different data interpretations from our electrochemical measurements, we see that there's a decrease in the concentration of hydrogen in our sample over the course of 10, 11 hours. We drop to about 40% of what we added initially. And this is an important observation because it shows that intermediate species are of importance at the timescales of hours. And if we're talking about irradiated fuel, then it might not be sufficient to just rely on thermodynamically stable species in order to describe the fuel. We might also care about kinetically quasi-stable species in the melt in order to understand apparent solubilities and apparent fluid properties. So this was an important observation here. And then so this illustrates an example for hydrogen, but similarly, we can also use these techniques for oxygen. That's an example trace for oxygen, so we can detect air ingress, oxygen ingress. If there is a new component, new metallic component that's being introduced into the salt, that might be an indication of an operation that is being done in the reactors. New components, if they haven't been salt flushed, especially if they have welded joints, they might have oxides on their surface, and so as they're introduced in the salts, those oxides dissolve, and maybe they can be detected with electrochemical measurements. And this is an example of detecting oxides in FLIBE using square wave voltammetry. And then from here, we're developing reference electrodes, which is what you see here. This is in collaboration with Ultramed, and we're developing printed electrodes, which is what you see here. This is a work done by Tony Consiglio, a student from our group, a prior student from our group, where he was designing, we have a nano fab center here at Berkeley, and so he did a lot of work to think about how we design the structure of these printed electrodes so that they don't delaminate due to differential thermal expansion. And then we do quite a bit of work on reference electrodes in fluorides and in FLIBE. Reference electrodes are pretty challenging in terms of material compatibility and stability, and so we do a lot of work on stable reference electrodes and understanding the stability of reference electrodes. And then the ones we're working with have pretty good stability to sub-millivolt over 10 hours. So we're pretty happy with that. And then we have a project with that's led by MIT to put our electrochem cells, our electrochem probes on a irradiated salt loop at the MIT test reactor. And that's the design here that you see that will be going on a T in upstream and downstream of the irradiated section on the salt loop at the MIT test reactor. And so with that, I also want to thank the students in our group, graduate students and undergraduate students, Christian Sclafanis, been working on the salt loops, and Michael works on the electrochemical sensors. Nathaniel works on speciation and salt properties. Ryan works on corrosion. Haley works on electrochem, so some of the work I showed was her work. Sasha works on the elemental analysis and spectroscopy. Lorenzo does a lot of work on graphite and tritium, and graphite chemistry at high temperature. And then Maxime works on graphite waste and waste forms. And I'm happy to answer any other questions.
Great, thanks, Raluca. So other questions? Further questions for Raluca?
I have a question, Raluca.
Yes.
This is Dan. Right before I was logging in, my computer said I needed to reboot, so I just joined Canon, our conference room. But anyway, on slide 28, I think.
Yes.
The diffusivity and the activation energy for one of the species was much higher for the in the reds right there.
Here.
The graph on the left.
Oh, the graph on the, yeah.
So two of those are lower activation energy, 37 and 42. Those are both tritium, and then the higher one is 177 is deuterium. Could isotopics play any part in that?
No, I don't think so. It's unlikely that the isotopics would have such a significant effect. The energy, the bonding energy, yeah, I don't think we can expect such a big difference between 40 and 177. If it was 160 to 165, maybe. But such a big difference, no, I don't think so.
Okay, thank you.
Are there other questions? So I think you partially answered one of my questions at the end, showing that you plan to kind of take the salt loop for irradiation at the MIT reactor, but it also looks like you had other ways of kind of testing irradiation behavior, like inserting tritium or hydrogen. Can you comment on ways that you can maybe understand the performance of irradiation without irradiating the salt?
Yeah, so for tritium, it was important to us to produce tritium in situ as opposed to equilibrating the salt with a gas. And so what we wanted to do is come up with a chemical reaction that would in situ produce hydrogen, similarly to how neutron activation reactions are in situ producing hydrogen. And so that's what we did there. We used lithium hydride as our reagent to in situ introduce hydrogen.
Okay, but otherwise you do need to irradiate to understand that behavior?
To understand what transient states might exist as a consequence of fission. Ultimately, yeah, it's important to have the irradiated salt, but along the way we can definitely work with non-radioactive surrogates and think about how do we introduce them in the salt so that their production is maybe representative of what might happen in a reactor as well.
Thanks.
Yeah.
Are there other questions? So I see Andrea has a question.
Hi, Raluca. Thanks so much for your talk. I learned a lot from it. So there's one question I had. You had a plot of the free energy versus the temperature.
Free and here?
Yes. So I was wondering, like how you would, obtain the free energy from the electrochemical experiment.
Oh yeah, thank you for that question. So if we look at this plot, for example, maybe let's look at the next one. Okay. So here we obtain a potential for this reaction, which is the H2 to H plus reaction. And it's 2 volts versus beryllium 2 plus beryllium. So how do we know that what is our reference? Our reference here is actually a nickel reference electrode. So this reference electrode is a nickel couple, or now we also work with silver couples, silver fluorides, silver fluoride. And so we measure potentials of reactions versus a reference concentration. And then we could convert that to a Gibbs free energy. And that's why it's so important to have a reference potential that's stable, so that the potentials I measure today can be referred to and compared to the potential I measure tomorrow. And they're all on the same thermodynamic scale. And then similarly, you can obtain activity coefficients. Again, if you have a constant reference potential, then you can obtain activity coefficients of different solutes in your melt. So activity coefficient of chromium in FLIBE, in an aluminum fluoride melt, and then you get your activity coefficients.
Okay, thank you.
Yeah, does that answer your question?
Yes.
Thank you. Are there any more questions for Raluca? Right, well, thanks, Raluca. Really appreciate it, hearing more about your work. And that wraps up today's webinar.
Thank you so much.